Chemical equilibrium. For most normal reactions, ones that go to completion, when we examine the contents of the reaction vessel after the reaction has stopped, we find all of the products present and all but one of the reactants present. This one reactant that is no longer present is the limiting reactant. The reaction stops because we no longer have that reactant. When we examine the contents of the reaction vessel for some reactions, however, we find some amount of each of the reactants and some of each of the products. We also see a system in which the amounts of these reactants and products are not changing. This type of reaction is called an equilibrium reaction. In order for the chemical reaction to occur, we must have a reversible reaction, that is, one that goes readily from the reactants to the products and from products to reactants. At equilibrium, reversible reactions must be able to occur in both directions. In part, this means that the products cannot escape from the reaction vessel. If there are gases present, then the system should be a closed system that does not allow the gas to escape from the rest of the reactants and products. In order for the forward reaction to occur, all the reactants must be present. In order for the reverse reaction to occur, all of the products must be present. Equilibrium is when this is true and the properties do not change with time. So the first definition of equilibrium is when all reactants and products are present and the properties of the system do not change with time. Equilibrium is a dynamic process. The reactions are continuing in both directions. The reason that the properties remain constant is that the two reactions are changing things equally. So the second definition of equilibrium is when the rates of the forward and reverse reactions are equal. You should note that we cannot actually measure these rates because the concentrations are not changing. Because at equilibrium, both the forward reaction and the reverse reaction continue to occur, when we have an equilibrium reaction, we use a double arrow to indicate that the reaction is reversible, and we will be dealing with an equilibrium reaction, not a reaction that goes to completion. The double arrow is read as in equilibrium with. Let's look at the equilibrium reaction, N2O4 gas in equilibrium with 2NO2 gas. We start with only N2O4 and no NO2. Here's a graph of how the rates of the forward and reverse reactions change with time. Since we start with only N2O4, the forward reaction begins at a high rate. The reverse reaction begins at a rate of 0 because there is no NO2 present. As the reaction proceeds, both the forward and reverse reactions are occurring. The concentration of N2O4 decreases, and the rate of the forward reaction decreases because of that. At the same time, the concentration of NO2 increases, and the rate of the reverse reaction increases as well. Eventually, the rates of the forward and reverse reactions are equal. When the rates become equal, we have reached equilibrium. Now let's look at a graph of the concentrations of N2O4 and NO2. Since we start with only N2O4, its concentration starts out high and decreases. The concentration of NO2 starts out at 0 and increases. Once we have reached equilibrium, the concentrations stop changing because the reactants are being produced by the reverse reaction just as rapidly as they are being used by the forward reaction, and the products are being made by the forward reaction as rapidly as they are being used by the reverse reaction. Note that, as is true in this case, the concentrations of the two substances are not necessarily equal at equilibrium. In fact, they usually are not. We know that we have reached equilibrium when the concentrations stop changing. Because the concentrations of the substances remain constant during equilibrium, there is a mathematical equation that expresses that relationship and a number that relates the amounts. These are the equilibrium expression and the equilibrium constant. Let's look at the equilibrium between N2O4 and NO2. Let's assume that both the forward reaction and the reverse reaction occur in a single elementary step. This may not actually be the case. The forward reaction is N2O4 gives 2NO2. Remember that for an elementary reaction, the rate expression is found from the stoichiometry of the reactants in the reaction. So the rate expression is rate sub F for forward equals K forward times the concentration of N2O4. The reverse reaction is 2NO2 gives N2O4. And the rate expression is rate sub R for reverse equals K reverse times the concentration of NO2 squared. At equilibrium, we know that the rate of the forward reaction is equal to the rate of the reverse reaction. So K forward times the concentration of N2O4 equals K reverse times the concentration of NO2 squared. Rearranging this equation to put the concentrations on the same side and the rate constants on the same side, we get K forward over K reverse equals the concentration of NO2 squared over the concentration of N2O4. Since the values of the rate constants are constant as long as the temperature doesn't change, then the ratio is also a constant, which we call capital K sub EQ for equilibrium. The ratio of the concentrations of reactants and products is sometimes called the mass action expression. The whole equation is technically called the equilibrium expression only when the system is at equilibrium. Since we started with the assumption that the forward and reverse reactions each occur in a single step, you might think that things would be different for multi-step reactions. This turns out not to be the case, as we shall see later in this lesson. It turns out that the form of the equilibrium expression is related to the stoichiometry of the balanced equation, even when we have a complex mechanism. So for this general equation, A molecules of A plus B molecules of B in equilibrium with C molecules of C plus D molecules of D, the equilibrium expression would be K sub C for concentration, or KEQ, or just K, equals the concentration of C to the C power times the concentration of D to the D power, divided by the product of the concentration of A raised to the A power and the concentration of B raised to the B power. You should note two things about this expression. First, the exponents of the concentration are the coefficients in the balanced equation. Second, the form has the products in the numerator, on top, and the reactants in the denominator, on the bottom. The general form products over reactants is a convention we use when we write equilibrium expressions. All equilibrium expressions are written in this fashion, with the exception of specially defined expressions.